Hello, in this video we're going to be working through some problems from the Review Collaborative covering chapters 7, 8, and 9. Let's go ahead and jump in here with a problem. Suppose that a random sample is going to be taken from a U-shaped population with a mean of 306.74 and a standard deviation of 53.807. For samples of size 26, what is the distribution of all possible values of the sample mean? Alright, so let's go ahead and start identifying some of the information that they told us so far. They told us that we have a U-shaped population right here, so that might come in handy a little bit later, so we'll underline that piece. They tell us we have a mean of 306.74, but what kind of mean is it? Well, it's a population that gave us that mean, so that's a population mean, so that's mu. And a standard deviation of 53.807, but again the same question, what kind of standard deviation is it? It came from this population, so if it's a population standard deviation, then that would be sigma. Alright, and then on to their question. They tell us that we have a sample size of 26, so if that is a sample size, then that would be n, so n equals 26. And then what is the distribution of all possible values of the sample mean? If we're going to do the distribution of something, it's good to know what that thing is, so sample mean is x bar. So they're asking us to come up with the distribution of all possible values of x bar. And we have some bad news right away with that, with an n of 26, because if n equals 26, that is in between 15 and 30. And that means we're working with a medium-sized sample, which is not ideal. So we start off with some bad news. We'd like to have a large sample. That's the easiest case, but we have a medium one here. But that's okay if we have the right kind of population. And the right kind of population would be one that is not severely skewed. And they're telling us that our population is U-shaped, which is a symmetric distribution. And symmetric and skewed are opposites. So if the distribution is symmetric, then it cannot be severely skewed. So let's make a note of that. So the population is U-shaped. And then why is that important? Because that is not severely skewed. So we've got good news there. We have a medium-sized sample, which isn't good, but the population is U-shaped, which is not severely skewed. And when you have a medium-sized sample from a population that is not severely skewed, then your x bar will be normally distributed. So based on this, we can say, therefore, x bar, which is our variable in this problem, will be normally distributed. You could say approximately normally distributed or just normally distributed. It's officially approximately. I would take either one though. And then when you say that, you've answered the main question. What kind of distribution do the sample means have? Those x bars are going to be approximately normally distributed. But there's infinitely many normal distributions, so we want to narrow that down to a single one by stating what the mean of the x bars would be. And it's x bars are variable, so it's the mean of the x bars we're trying to give. And the formula for that, which is on our formula sheet, is that mu of x bar equals mu, which we've already identified as 306.74. And then we'd want to give the standard deviation as well. And our variable is x bars, so we're looking for the standard deviation of the x bars. If you look at your formula sheet, that is approximated by sigma over root n. And we have our sigma up above. It's 53.807. Divide that by the square root of our sample size, which was 26. And then we'll have our standard deviation. So bring in the calculator for that last part. 53.807 divided by the square root of 26 is approximately 10.552. So remember that when you are calculating standard deviations and you need to round them, you should put at least 5 significant figures. So we've got 2 in front of the decimal and 3 after, so we're okay there. Alright, so that takes care of part A. Alright, moving on to part B, how much sampling error should he expect from the point estimate? So we're talking about sampling error, but this is before we do the sample. They're saying how much would we expect, so they're asking us about expected error. So the opposite of getting an expected amount of error would be to get an unusual amount of error. And we should be comfortable with the idea that something is unusual when it's more than 2 standard deviations away from the mean. So hopefully that reminds you then that expected error is anything that's less than 2 standard deviations. So our expected error, go ahead and label that as EE, would be anything that is less than 2 standard deviations of the variable that we're working with, and our variable in this problem is x bar. That's going to be our estimate. It's going to be x bar. So our expected error is less than 2 standard deviations of x bar, and that means our expected error is less than 2 times the standard deviation of x bar, which we computed right up there, 10.552. And if you throw that into your calculator and do the doubling, you will get an expected error of less than 21.104. Make sure at the end of this problem you're clearly stating that your expected error is less than a specific value. It's common for people to make the mistake of at the end saying their expected error equals this, but it would be unusual for our error to be 2 standard deviations. We expect it to be less than that, so make sure that less than makes it into the end product. All right, let's move on to the final question on this one. Determine the probability that a sample of size 26, which is the one we've been talking about so far, will result in a point estimate with a sampling error of less than 15. So they want us to do a probability question. So some sort of probability question is being asked. And the point estimate is that x bar. So eventually this is going to become a probability question about x bar. That's what we use for our estimates when we're dealing with means. But they want the probability that the sampling error, so we'll write an SE for that, would be less than 15, so less than 15. So there's a direct translation of their probability question. But notice that doesn't have the x bar in it, so we have to think about what does that mean for x bar to have sampling error of less than 15. Well, we're using x bar to try and estimate mu, and we know from up here at the very top that mu is 306.74. So if we come within 15 of that with our x bar, then we would have met the requirement they're asking of us. So what we want to translate this to is the probability that if you took the real mean, 306.74, and you subtracted 15 from that, that would be less than x bar, which would be less than the real mean 306.74 plus 15. So here's the probability that our point estimate, x bar, would be within 15 of the truth, which means it would have a sampling error of less than 15. And then you can subtract and add that 15 to finish off the translation into probability notation. So this is the probability that 291.74, that's just doing the subtraction, is less than x bar, which is less than 321.74, which is what we would get if we did the addition on this side. And now we've got a probability question about x bar, and x bar is approximately normally distributed, and we know the mean and standard deviation. So essentially this has just become a Chapter 6 question, a probability question about a normal distribution. So I will draw a normal curve because in part A we did say that x bar is normally distributed, so this is a graph for x bar. The mean of a normal curve is its mean, and we said in part A the mean of the x bars was 306.74, and then we want to know the probability that x bar will land between this 291.74 on the left and 321.74 on the right. We don't really know exactly how far out those numbers are in terms of z-scores yet, so I'm just drawing this one on the left because it's smaller and that one on the right because it's bigger, trying to do it roughly symmetric because I know I added and subtracted the same amount. And then if we can find that area right there, we'll have answered that probability question. And the way that you find areas is to use the normal CDF, but we use z-scores when we do that. So let's do a z-score for this right-hand side right here. This would be our z2, I guess. So z2 would be that boundary, 321.74, minus the mean, 306.74, divided by the standard deviation, but we have to be real careful here because there's 2 standard deviations. There is the 58.807 right there, but that's sigma, and we're doing a probability question about x bar. So we need sigma of x bar as our denominator. So I'm going to divide here by the 10.552. And we should be getting pretty comfortable at this point with doing z-scores on our calculator, but just a reminder, we need parentheses around the top. So 321.74 minus 306.74 divided by 10.552 gives us a z-score of 1.422. And because of the symmetry, the z on the left would just be equal but opposite. So our z1 over here should be negative 1.422. And once we have the z-scores, we can use normal CDF to get the area, which will be that probability. So normal CDF from the left boundary, negative 1.422, to the right boundary, positive 1.422. So we can just go to the calculator on that, and we'll have our answer. All right, so we bring in the calculator. Second distributions, go to normal CDF, put in our left boundary, negative 1.422, and our right boundary, positive 1.422. Can think about empirical rule if we want. More than one standard deviation, or one standard deviation would be about 68%, two would be 95%, so we should be somewhere in between 68 and 95%. So an answer like 0.8450 makes sense, and it would be a 50 because of the 7, rounding that 49 up to a 50. So there's our answer. We were looking for a probability regarding x bar. That would be this area, so when we found the area, we answered the probability question. All right, that wraps up the first problem. All right, on to the next one. A poll was taken in 2010 of 1,098 Americans who purchased green products. The results showed that 575 of those surveyed agreed with the statement, global warming or climate change is occurring and it is primarily caused by human activity. Find a 99% confidence interval for the true proportion of all green consumers who agree with that statement. All right, so we're doing a confidence interval. We've got our confidence level right there, 99%. So I want to write down the formula and start assembling the pieces and go to work. But I need to know, am I in mean land or am I in proportion land? And it is a confidence interval for the true proportion. So the true proportions are referenced to the population proportion P. So that's what we're trying to end up with, an answer for what do we think P, the population proportion, is. So we are in proportion land on this one. So if you look at your formula sheet, you will come up with the formula P hat plus or minus Z star times the square root of P hat Q hat over N. Definitely encourage you on all these problems to start off by writing the formula and look at your formula sheet for it so you're not accidentally getting any of the wrong pieces in there. But it's good to start with the formula because then you know all the pieces that you need. You need P hat, you need Z star, you need N, you can get Q hat from your P hat, but it's kind of just a list, like here's all the things I need. So let's go ahead and start off with the Z star. That comes from our confidence level, which on this problem is 99%. So if we have 99% in the middle, then there's 1% left over, but that has to be split among the two sides. So take that 1% or 0.01 and cut it in half, and you would have 0.005 on both sides. I think you should do a quick kind of sanity check on this to make sure that when you add across that you get the number 1. Sometimes I see people put 1% on both sides. Now your total would be 101%. So make sure you're thinking about that. And it's a Z star that we're looking for. So what you want to do is go to your formula sheet, think about the area in the tail, 0.005, so that's this column. If you stop at any row here, you're doing a DF and therefore a T-score. So this is a Z-score we're looking for, so find the T column, but go all the way down to the bottom, and that will be your Z-score. So 2.576 is going to be my Z star that goes with 99% confidence. And then I need my P hat. P hat is X over N, the number of successes by the number of tries. We had 575 people agreeing with the statement out of 1,098 that we asked the question to. And if you do the division on your calculator for that one, you will get 0.5237. So let's see, what have we got? We've got a P hat, we've got a Z star, we have our n up top, 1098, right? We can see our n right there is 1098. And then q hat would be 1 minus the p hat, and if you do 1 minus the 0.5237, you get 0.4763. So if we want, we could write the n down as well, 1098, but we've already kind of used that. So we have all the pieces right there, and then we just start going to work over here on the other side, working out our confidence interval. So start out with p hat, which is 0.5237. That being called a p hat because it came from a sample, and a sample proportion has no chance of being equal to the population proportion. So we need to give ourselves some margin for error, which is this plus or minus piece. To be 99% confident, we have to go out a little more than 2.5 standard deviations in each direction. And our estimate of the standard deviation of p hat is the square root of p hat q hat over n. So we will plug in the p hat, 0.5237. Multiply that with the q hat, which is 0.4763. And then divide all that by our sample size, which is 1098. When you're doing one of these, we want to show the margin of error. So just take the p hat piece and just copy it down, 0.5237. And then we have the plus or minus still, and now we're going to work out what our margin of error is. So bring in the calculator for that. And 2.576 times the square root of all three of those things. So the calculator is opening the parentheses on the square root. We don't want to close that set of parentheses till all three numbers are in there and therefore under the square root. So 0.5237 times 0.4763 divided by 1098. And that is not our answer to the whole thing, but just the margin of error piece. We're supposed to match decimals with this and our point estimate, in this case p hat. So there's 1, 2, 3, 4 decimals there. So we do 1, 2, 3, 4 decimals on our margin of error as well. We are counting the 0 here because we're counting decimal places, which is what you do when you're doing addition subtraction. And then that's pretty much all the work. We just need to turn that into an interval for p. So we're 99% confident that p is in the interval that goes from a lower end of 0.4849 to an upper end of 0.5625. And there's our confidence interval for the true proportion of all green consumers who agree with the statement that global warming or climate change is occurring and is primarily caused by human activity. All right, and now moving on to part B. A year earlier, it was found that 58% of green consumers agreed with that statement. Can we be 99% confident that the true portion of all green consumers who agree with the statement has decreased from the 58% that it used to be? Explain using your answer from part A. So here's our answer. So looking at that answer, does it seem like 58% is still a reasonable possibility for the truth, or does it look like it has decreased? In order for this 58% to still be a reasonable possibility, 0.58 would need to lie between these two boundaries, and it does not. And then both of these boundaries are below 0.58, which means the entire range is below 0.58. So what is p? We're not entirely sure, but we're confident it's in this range. This entire range is smaller than 0.58, so we can be confident that it has decreased. So it looks like this is going to be a yes. I said a lot of words there, so I think it's easier to write this out in symbols. So yes, because if p is an element of 0.4849 through 0.5625, then that implies that p is less than 0.58 because everything in that range is less than 0.58, and that implies that p is less than 58% and thus has decreased from what it used to be, because it used to be 58%. Couple quick notes on this. I'm saying if p is an element of that instead of because p is an element of that, because we're not 100% confident p is in that interval, just 99%. But that's okay, because they're just asking us, are we 99% confident it has decreased? So we can use that. The other thing that people do a lot of times is they'll just put a less than 0.58 right here, but an interval we shouldn't say is less than 0.58. It's p we're being asked about, so p is in this range, therefore p is less than 0.58. So make sure you still have the p in this inequality statement as well. All right, moving on to part C. Let's use the interval from part A to make a conservative guess for what the population proportion is. So that's going to be our PG. And then once we have that, determine the sample size we need to lower the margin of error to at most 1.5%. So there's two things they're asking us to come up with here. A guess at the population proportion. So if we're guessing at the population proportion, that's going to be us trying to figure out a value for P sub G. And we're doing that because they want us to determine the sample size, which is n. So we're clearly in proportion land, and we're looking for sample size. So if you look at your formula sheet, there's a line in Chapter 8 for confidence intervals that is about averages, and then there's another line that is about proportions. And we're in proportion land, so we're going to use this formula right here because we're looking for n, and that makes sense because it has PG in it. And they told us to make a guess at the population proportion. So that one seems to fit. So let's go ahead and write down the formula we're going to use, and then we'll start thinking about what the pieces are. So I'm going to use the formula n equals a guess at p times 1 minus that guess, and then that's going to be times z star over e, and that quantity is squared. So if you think about the pieces we need, z star we have, you might feel like we have n, but that was an old n. Now we're trying to look for a new n. So this will be our end answer. We need a pg, and they said use this answer to make a conservative guess at p. All right, so using part A, if p is an element of 0.4849 to 0.5625, 5625. A little dyslexia going on there, apparently. Let's clean that up. All right, so what should be our guess at P? And our rule says that when we're given a list of possibilities, we should guess the number in that range of possibilities that is closest to 0.5. When I asked people in class about this recently, a lot of people said this number because they're just thinking about the 2. But this is a range of infinitely many numbers that goes from 0.489 all the way up to 5625, but includes all the things in between as well. So if you're considering everything in this range and saying what's closest to 0.5, well, 0.5 is in that interval. So 0.5 should be our guess. All right, so we got our PG. Our Z star is still for 99% confidence, so we're still going to use the 2.576. Margin of error was given to us. So right here, they said they wanted a margin of error of at most 1.5%. So if we pulled that down, they want a margin of error of 1.5%, but you don't put it in percentage form, you put it in decimal form. So we would use a margin of error of 0.015. So now we have all the pieces. PG is 0.5, 1 minus PG, just uses this number again. Z star was from up above, so that was 2.576, and the E we just figured out. So let's figure out our sample size as well. So N is going to be our guess at P, 0.5, times 1 minus that, which would also be 0.5, and then times our Z score, which is 2.576 if we're doing 99% confidence, and we're sticking with that. And then divided by E, which is 0.015, and then that whole fraction would be squared. And I wrote that down basically in the way it would look on our calculator. So let's go ahead and enter it in. So 0.5 times 1 minus that, which is still 0.5, times parentheses 2.576 over 0.015, and then squared. The parentheses making sure I'm squaring the whole fraction. And I get 73.08. However, sample size can't be a decimal, so we need to make a whole number out of that. And most people would tend to think, well, 73 is closest. But this is one of those special cases where we have the rule that says always round up when you're calculating sample size. So we would go with 7374. So there's your answer, and then just a quick reasoning behind that. They said they wanted our margin of error to be at most 1.5%, and the bigger our sample size, the smaller our margin of error, and vice versa. So if we were to round this down, well, let me say something different first. This decimal value is supposed to give me that margin of error. If I rounded it down, the margin of error might go up and be bigger than this, and they said at most 1.5%. If I round this up, the margin of error will get smaller than that, and we never get in trouble for too much error. So that's just kind of a brief explanation for why it is that we always round these up instead of down. We don't do that with most numbers, but we do it with sample size. All right, next problem. In spring 2008, mobile subscribers sent and received an average of 537 text messages per month. During that same time period, a sample of 58 college students produced a monthly average of 812.3 texts with a standard deviation of 408.15. Does the data provide enough evidence at the 1% significance level to show that college students on average text more than mobile users in general? All right, so first of all, on average. So we're in mean land. And then, does the data provide enough evidence at the 1% significance level? Phrases like significance level only show up when you're doing hypothesis tests. So it seems like we're doing a hypothesis test. It seems like it is about the mean. It's a problem that has context to it. So when we do that, we do all 6 steps of the hypothesis testing procedure. So we'll start off with step 1, write out the null and alternative hypotheses. And because we're in mean land, HO will say that mu equals something. So we go through and we read the problem, we look for some value that seems like an old value, a comparable value, a claim value for the mean. And it says that in spring of 2008, mobile subscribers sent and received an average of 357 text messages. So that's definitely an average. So it's a number that we could put there. Now there's another number right here that says an average, 812.3. So in a way, both of those might seem like candidates, but if you look at what this number is right here, it says this sample of 58, so what is that telling us? N equals 58. Produced a monthly average of. So this sample produced this average. If this is a sample average, then this is X bar. And we never put X bar in HO. So given those two choices, this is one that was a claim value or an old value or a comparable one. It looks like we're going to compare college students to mobile users in general, and there's the number for mobile users in general, so 357. And then what is it we're trying to show? That college students on average text more than. So we want to show that for college students it's more than 357. So our default starting point is maybe for college students it's the same as for everybody else. And then for H1 we're going, no, are you kidding me? Have you seen college students? They're texting all the time. It's probably greater than mobile users in general. And then for 2, we just state our significance level, which I already underlined is 1%, but we would list that as a decimal. I'm going to draw my typical little fence around steps 1 and 2, and just remind you that that's steps 1 and 2 are supposed to take place before any data is collected. So one of the reasons that matters is that's the reason you can't use 812.3 in HO or H1, because if you're supposed to be setting up HO and H1 before you take a sample, then you can't use the sample value in this line because you wouldn't have a sample yet, so you wouldn't know what that value was. So anytime you find yourself trying to put X bar or P hat in that spot, that means that you're kind of thinking out of order. So those claim values have to come before the sample somehow. All right, so there's steps 1 and 2. So for step 3, we're in mean land, so our test statistic would be a t-score. It would be our sample mean minus the claimed mean divided by the standard deviation of X bar, which we're going to approximate with S over root N. So then we can just think, do we have all those things? X bar is right there. The claimed mean is the 357. S is the sample standard deviation, and this sample produced a standard deviation of 408.15, so that's S. And then the N is right there, 58. So we do have all those pieces, so we can plug them in our sample. 812.3 was the average, minus the claim value of 357. And what you should think right away is like, wow, that's a big difference. right? Somebody's trying to tell me the average for this group of college students is 357, but in my sample I got 812. That seems like a huge difference to me. So I'm leaning towards reject right now, because if the sample value is really different from HO, that makes it hard to believe that that HO value is the true one. So I'm leaning towards rejecting it, but I'll have a better sense of how far apart they are when I complete the t-score. So divide by S, which itself should be divided by the square root of n. All right, and then that'll produce our t. So this is a little bit of a tricky one in the calculator. When you're doing fractions, if you have more than one number in the top, you should put parentheses around that. If you have more than one number in the bottom, you should put parentheses around the bottom. So we're going to need parentheses around both. So 812.3 minus 357, parentheses around the top of a z-score, t-score, very typical. But when you divide, you need parentheses around the bottom too. So 408.15 divided by the square root of 58. The first closed parenthesis is on the square root, the second one is on the denominator. All right, so you get a number that can freak you out a little bit maybe, because it's so big. If you're thinking of this like a z-score, to say things are 8.5 standard deviations apart is so big. Let's see, the rounding on this looks like it could be a little tricky. It's 495, well, not that tricky, it's just 495, but the 5 is followed by a 5, so we'd round it up and get a 6. So again, that's a huge t-score, but this was a huge difference, so it seems to fit. When I saw the 812, I was thinking I should reject HO. When I see that my sample value and my claim value are about 8.5 student deviations apart, I should be even more leaning towards rejecting HO. So things are fitting together. So I'm definitely leaning towards reject HO. And as soon as I start considering rejecting HO, I'm thinking that I could be putting myself at risk for a type 1 error. So I want to calculate, if I were to reject HO here, how big of a risk would that be of making a type 1 error? So this is a t-curve. The df is 1 less than the sample size. So our df on this one would be 57 because the sample size is 58. So we're just going to subtract 1 from that. And then put 0 in the middle, which represents the claim value 357. Put 8.496 on our picture, representing 812. Really, that should be off my piece of paper, right? This is about a t-score of 3, so 6, 9, we're just way out there, right? But I'm going to put it right here just so it fits on the picture. And then, let's see if we can get a color that'll show up. Our p-value would be the area to the right of that, and I've drawn that a little bigger than it really is. In fact, a lot bigger than it really is, because we're so much further out there. But we are looking to this small area to the right of that number to be our p-value. So our p-value would come from calculating TCDF from 8.496 to infinity with 57 degrees of freedom. So our p-value is approximately, we bring the calculator in again, and it's just, if you think about the picture, it's real small, and then think about the fact this 8.496 should be even further to the right. This is a tiny, tiny number we should be getting. So we go into distributions, we look for TCDF, our left boundary 8.496, we have no right boundary, it's infinity. I have infinity stored into I. If you have not done that, then go back and watch videos for how to store it, or just put a big number like 1,000 or something in there. And then we have 57 degrees of freedom. So if I enter that in, I should get a small number, and it seems like at first I get a big number, 5.18, but E negative 12 means move the decimal 12 places to the left. So that 5 is the 12th digit after the decimal place. So there's 11 zeros and then that 5. We typically only write 4 decimal places, so I can say my p-value is approximately nothing. So a very key piece in the process here. So is this. All right, so it's time to make our decision. Decisions and conclusions time. So in step 5, we're either going to reject HO or we're not. When we saw this big difference, we were thinking, wow, HO looks false because these are so far apart. The t-score confirmed that they really were indeed very far apart. I don't think I mentioned this back here, but I did the area to the right, not because I landed on the right, but because it was a greater than in H1, so it was a right-tailed test. So I needed the area to the right, and the area to the right was real small, which represents my risk of making a mistake if I reject HO. So just a reminder, I'm on H1's team, So I go into this process wanting to reject HO, and I will do that if the evidence is strong against HO and the risk of rejecting being a type 1 error is low enough. You can't really get lower than that 0. So I wanted to reject HO, the evidence was strong, the risk was low, so I am going to go ahead and reject HO because there's an acceptably low risk of making a type 1 error, essentially almost no risk that I'm making a type 1 error. What we're saying is there's almost no chance that if HO is true, that you would have got a sample value like 812.3 just due to random variation. But we did get this value of 812.3. We don't think it could have been because of random variation, so what we think is the reason we're getting that is because the real mean is actually bigger than 357, so we're rejecting HO in favor of H1. So in step 6, we're going to say we did have enough evidence at the 1% significance level to show, and what were we trying to show? That mu is greater than 357, or in words, to show that college students text on average more than mobile users in general. All right, so that finishes up the hypothesis test, and we just have a follow-up question, so let's go ahead and look at that. What effect do you think this result would imply about a survey of adults in the US that required respondents to text in their responses? So we're not talking about this survey now, we're talking about some new one. Who knows, right? There's like, do you approve of this policy, that policy? Do you like watching this show, that show? Who knows what they're asking, right? But they're doing some sort of poll and they're asking people to text in their responses. Well, what this shows us is that college students are more likely to be texters than mobile users in general. So if you are going to, instead of having a random sample, have some volunteer response survey that specifically asks people to text in, then because college students are more into texting, they might be more likely to respond than other people, and that means that your survey is going to be biased towards the opinion of college students, whatever that happens to be on that topic. So because our hypothesis test shows that college students text more, it's likely that the sample that we get would be biased towards the opinion of college students. So when you're talking about your sample, somebody asks you to describe it, and you use the word biased in there. That's never a good thing. So we're not supposed to do volunteer sampling. We're supposed to do some sort of simple random sampling that gives every person in the population an equal chance at being involved. But if some people are more likely to respond to a text than others, that takes that away, and then we get a bias in there. So we're always looking for random samples, so we'd always want to be careful to avoid techniques that create bias. All right, that wraps up this problem.